Hi, it's Ms. Marat here with help on today's assignment, the Unit 6, Lesson 5, practice problems. You're doing numbers 1, 2, 3, and then 5 and 6. All right, so number 1, a rocket is launched in the air and its height in feet is modeled by the function h. Here is a graph representing h, and then this is time here on the horizontal axis. All right, so the first question is to select all true statements about the situation. So first, the rocket is launched from a height less than 20 feet above the ground, versus B, the rocket is launched from about 20 feet above the ground. So on the y-axis, or the vertical axis right here, is where the launch is. And it looks like it's actually less than 20 feet, because if this is 40, then 20 would be this line right here. And so we'll say A, that it was launched from a height less than 20 feet. C, the rocket reaches its maximum height after about 3 seconds. So the maximum height is going to be like the highest point, and that looks like about 3 seconds. So I would circle that. And then the rocket reaches its maximum height after about 160 seconds. No, the 160 is actually the height in feet. So the maximum height is about 160 feet at about 3 seconds. So don't select D, but select E. The maximum height of the rocket is about 160 feet. All right, on number 2, it's about a baseball travels D meters T seconds after being dropped from the top of a building. The distance traveled by a baseball can be modeled by this equation. D equals 5 times T squared. Okay, so 5 times T squared. So if the time is 0, I'll just put my calculator here. I'm going to use the equation. So to figure out the distance, it's 5 times t squared. Okay, so if t is 0, 5 times 0 squared is just 0. It hasn't dropped yet. Okay, and then at 0.5, so 5 times 0.5 squared is 1.25. So after half a second, it's dropped 1.25 meters. And then 5 times 1 squared is 5. So after 1 second, it's dropped 5 meters. And then 5 times 1.5 squared is 11.25. So after 1.5 seconds, it's dropped 11.25 meters. And then finally, 5 times 2 squared is 20. And so after 2 seconds, it has dropped 20 meters. So next, I'm going to plot the data on the coordinate plane. So we have time on the horizontal axis and distance traveled in meters on the vertical axis. So our points are 0, 0, and then 0.5, 1.25. I'm going to estimate about right there. 1, 5 is right here. 1.5, and then 11.25. I'm going to estimate about there. It looks like the points are curving and not lining up in a straight line. And then 2 is up here at 20. So for part C, is the baseball traveling at a constant speed? And explain how you know. So I would say it's actually part B. This is a typo, sorry. Part B. This isn't a question. Okay, so is it traveling at a constant speed? So a constant speed would mean that the points like all line up in a straight line. And so no, it's not a constant speed because the points don't line up in a straight line. Instead, it's getting faster and faster. If you look at this and kind of connect the dots a little bit, and it makes a curve, and they're going to get faster and faster until the baseball reaches the ground. Okay, on number 3, a rock is dropped from a bridge over a river. Which table could represent the distance in feet fallen as a function of time in seconds? So one thing to note is that 4 tables here. This is the distance fallen, okay? So when you drop something, how far it has fallen should increase as time goes on, right? So I know it can't be table C or table D because those are both decreasing. So if the question was like that this column was how far away it was from the ground, that would make sense. But how far has it fallen? Those values should be increasing. So it's going to be one of these. And so I know that when something drops, that it gets faster and faster as it gets further and further away. As time goes on, it gets faster and faster because of gravity. And so if I look at, well, how are these tables changing? It looks like on table 1, what's the change at each step? So obviously from 0 to 48, it's 48. And then from 48 to 96, it's also 48. And from 144, or 96 to 144, also 48. So this is changing at a constant rate, 48 each time. So I don't think it's going to be table A. When I look at table B, I know 0 to 16 is a change of 16. And then 16 to 64 is a change of 48. And then 64 to 144 is a change of 80. So I think it's a possibility to be table B. And I think that because it is getting faster and faster, it's traveling further each second. And so that would be more like in line with my thinking about how that object would gain speed because of gravity as it free falls. So we're going to select table B. All right. Number 5, select all of the expressions that give the number of small squares in step N. All right. So, okay, so I'm looking at these patterns, and so I'm thinking, okay, maybe I should think about, well, the total. So 2n. So if it was 2n, then step 1 would have 2 squares, step 2 would have 4 squares, and step 3 would have 6 squares, okay? And then if I look at this, oh yeah, step 1 does have 2, but then step 2 has 6 squares, and step 3 has 12 squares. So it can't be 2n. Next one is n squared. Well, 1 squared is 1, 2 squared is 4, and 3 squared is 9. That also doesn't match up with the numbers up there, so not B. C, n plus 1. 1 plus 1 is 2, so it works for the first one. But 2 plus 1 is 3, not 6, so it's not C. D, n squared plus 1. 1 squared is 1, plus 1 is 2, so that works. 2 squared is 4, plus 1 is 5. So that one doesn't work. Okay, and so we have a few more left. On E, n times n plus 1. So when I look at this figure, I see this dimension is 2 and this is 1. This is 3 and this is 2. and this dimension is 4, and this is 3, that way, okay? And so the step number here matches up with one of the dimensions. So this one would be n, and this one is one more, so this would be n plus 1. That happens in step 2 as well. The 2 would be the n, and the 3 would be the n plus 1. And it happens here again. The 3 is step 3, so n is 3, and 4 is one more, so n plus 1. So definitely E. And then when I look at F, I am thinking to myself, could it be that? Could it be that? Well, let's use a different color highlighter and see if I can make n squared plus n make sense, okay? So I'm first going to color in n squared. So for step 1, 1 squared is just one of these. Step 2, 2 squared is 4. 1, 2, 3, 4. So there's n squared. And then step 3, n squared is 9. 3 squared is 9. And so that's this much of the square. And then again, I notice, oh, there's 1 square here, which is the same as the step number, n. There's 2 squares here, which is the same as step number, n. And then there's 3 squares there, which is the same as that step number, n. So this part is n squared. This part is n squared. This part is n squared. And then the white section on each of them is n. So n squared plus n is a good one. That works. And then for the last one, n plus 1. Okay, so in step 1, we'd have 1 plus 1 plus 1, which is 3, and there's only 2 squares in step 1. So E and F are the only two correct expressions for this pattern. All right, and then finally on number 6. Okay. On number 6, it says a small ball is dropped from a tall building. Which equation could represent the ball's height h in feet relative to the ground as a function of time t in seconds? Okay, as I'm looking at this, I notice that a is a linear function, right? We're so familiar with linear functions. Starting value is 100 and it's changing by 16 every second. This can't be a linear function because the ball will get faster and faster as it approaches the ground, and so it's not going to be dropping at a constant rate. So it's not A. And then for B, so the ball is being dropped from a height of 100, and then we see this minus 16 t squared. So that t squared is going to get bigger and bigger, which means it'll travel by more and more each time. So it is B. And then just to kind of wrap this up, C is an example of an exponential function. I know we haven't really worked with exponential functions much at all this year, but it's not going to be C. And then D, interestingly, what happens here is that this would actually imply that the ball's getting slower as it approaches the ground, because as the value of t increases, the whole fraction will get smaller and smaller, and so you're taking less away each time, so it's not D. But this is the one, this is the quadratic. All right, and so that is the end of your assignment. I hope you found the video helpful.